So the next talk is by Eduardo Mendes on Markov interacting importance samplers.
Hi, thank you. Can you all hear me? Yes, good. In this talk, I'm going to introduce a new sampler that me, Robert, and Marcel developed, I think it was maybe late 2014, and last year we put some work on it. Well, it's still work in progress. This is a preliminary version. We have some good ideas in here, but if you can contribute, it would be great. So let's start. The outline is pretty standard. I'm going to first say what's my contribution. Then I'm going to talk a little bit about the main building block of the algorithm, which is called condition importance sampler. Then I'm going to explain the algorithm, talk a little bit about estimated expectations, which is one of the biggest advantages of our method, and then some illustration. Okay, so we propose a new MCMC algorithm, and it's based on, instead of sampling from a proposal distribution, you construct an importance sampling approximation of a proposal distribution, and then you sample from it. It's alternative to Metropolis Hastings. It's not really alternative because it is a Metropolis Hastings algorithm, but it's a different way of thinking about it, as opposed to construct a proposal distribution, sample this proposal, and iterate sequentially. We want to construct an approximation to this proposal and then sample from this approximation. As you're thinking, there is an overhead in constructing this approximation, but we can actually use all the particles involved in this construction. The nice thing is that we can use the variance reduction techniques that are very easy to apply in importance sampling methods in this new algorithm. And it will give us a large variance reduction in estimating moments. Our sampler can be written as a Gibbs sampler. So it's quite simple to break large target densities in smaller target densities and then target the smaller densities. So instead of having a very high dimensional importance sampler, we have a smaller dimensional importance sampler that iterates and has the name Markov interacting importance sampler. So we have importance samplers interacting in a Markovian way. And finally, this construction, because now we have a Markov chain, we can think about local proposals for importance sampling as opposed to just a global proposal as we usually do in these settings. So let's start. Importance sampling, for those of you who are not very familiar with this technique, is based in this simple observation. We have a, yes. We have a target integral here, expected value of f with respect to the distribution pi. And what we can do, we can just multiply and divide by q, and now we have another expected value. So we have the expected value of pi over q times f with respect to this new density q, which is our proposal. We can approximate this integral here using the latter, meaning we sample, we use the law of large numbers, of course, we sample from q, and then we construct what we call the importance density approximation based on the empirical distribution of the data. Well, the performance of these methods depend heavily on the variance of the weights, and there's a lot of work on reduce the variance, and some very, very smart people working these methods. I can see one of them here, I believe. And it's amazing. I think importance samples, when they work, they are amazing. But constructing proposals can be challenging. But we can apply variance reduction techniques. So if you manage to construct a reasonable importance sampler, you can apply variance reduction techniques, and we will obtain a very good estimate of your moment. As I said, in high dimensional settings, and I'm being very loose in high dimensional here, it can be a challenging task. So what we propose is a different way of approaching this problem. So we want to construct, we want local proposals. We want to construct importance samplers to be used within a an MCMC scheme. So we need to sample from an importance sampling approximation. So the question is, how can we implement an importance sampling approximation to a target density pi that provide unbiased samples? And our answer is what we call a conditional importance sampler. We see that this entity only lives within an MCMC scheme for a very good reason. But again, because we are within this MCMC scheme, we go a bit beyond the simple importance sampling, and we manage to have local exploration, something that's not usually possible in importance sampling schemes, only in a bit more advanced importance samplers. So how do we construct the conditional importance sampler? At each iteration of the MCMC algorithm, we will sample one particle xk conditional on the current value of my chain. Then I will sample the remaining n-1 particles conditional on this xk. I also introduced a new auxiliary variable called xi that will help in bounding the weights and also help with the local exploration of the method. Okay, so here's the algorithm, fairly simple. I first sample this auxiliary variable from some density that I have to be able to evaluate up to normalizing constant. Then I propagate y to xk, so xk is propagated directly from y, conditional on the xi, as you can see. And then I sample the remaining x's, the remaining particles, conditional on the xk. Here, I'm implying that the x's are conditionally independent. That may not be always the case. Okay, here's just a simplification of the algorithm, so I can explain how it works. Now, how can I construct an approximation? How can I approximate moments using this conditional importance sampler? Well, I have to construct a weight, which in our case given by wi, which is m over q, just like in the importance sampling case. But now we also have the eta multiplying that, as I said, has a role of bounding the weights when needed. Of course, you don't need that. You can just drop eta, and the algorithm will still work. The empirical approximation to pi is given by the x's and the corresponding weights. And the moment is essentially the same formula we had in the importance sampling case. Okay, so I said I want to construct unbiased sample. I have to define an augmented space in which I'm working. And the augmented space has all the variables involved in my importance sampler on the top of k and y, which is my current state in the Markov chain. And I define this augmented density that essentially has k sample uniformly from a uniform, y sample from the target. Again, as I said, it lives inside an MCMC algorithm, so eventually it will converge, so it's a reasonable thing to assume. And then we have our conditional importance sampler. One important result is that the expected value of our importance sampling, of conditional importance sampling moment estimation is unbiased. That's not usually true in importance sampling, but in our case, it is. So we managed to accomplish what we wanted. On top of that, we can calculate the marginal, the conditional k given the conditional importance sampler, and that's w. So it means that if I sample k with probability proportional to w, I have an unbiased sample from my target, just like I wanted. And the marginal distribution of y is my Markov transition kernel, the conditional distribution of y, sorry. So that also implies that we can sample from our our augmented target using a Gibbs sampler. It's a very simple Gibbs sampler. And that's what we call the Markov interacting importance sampler. So we have this Markov chain, and we're interacting approximation, importance sampling approximations. So in the first step, we construct the conditional importance sampler approximation, and then we sample one observation from this approximation, just like we wanted originally. One important thing here is that you can actually draw draw K using any using a Markov transition kernel. You don't really need to sample from like with probability 1 over W. Because a Markov transition kernel, and you may have improvement in the mixing of your sampler. And finally, you propagate your XK. Okay, the Markov interacting importance sampler, as I said, is a Gibbs sampler targeting the augmented density I had originally. So it's a very straightforward Gibbs sampler. So that's what I said. It's not really, it's not alternative to Metropolis Hastings. It's just not a way to look at it. That may be useful in some settings, and we hope it is. Okay, now I give a lot of like abstract formulas. Let's pick a couple of examples. The first one is assume I want to approximate my target using simple importance sampling. So I have a proposal distribution K, and the way it goes is given some initial state Y and K, I first sample n minus 1 particles from Q, and then I sample particle xk. I set it to be equal to Y, to the current state of the Markov chain. It's equivalent to use a identity kernel as a Markov transition kernel. Then I draw K, one particle K, with probability proportional to the weights, and I set Y to be this particle I just sampled. Now, as I said here, I'm simplifying a little bit the algorithm, but you can have enthalpy variables, for instance, and that's really not a big deal. Now, it's a very simple example. This algorithm has been explored in a couple of settings, especially particle Gibbs, and all the theory behind particle Gibbs is based on on this instance of the algorithm, but we can go beyond that. We can have a random walk proposal, or what we call a random walk proposal. In here, in the random walk proposal, we sample xi as an auxiliary variable, and we say that eta and q are symmetric distributions. Then, so we sample xi, then we sample all n minus 1 particles and set one particle to be yt minus 1, the current state of the Markov chain. Now, the weights associated with each particle are only mxk, which in a Bayesian setting will be the likelihood times the prior. So just like in the random walk algorithm, we had the ratio of likelihood times prior. In the Markov interacting importance sampler, our weights are given by the prior times the likelihood, as we would expect. All right, that's the basic algorithm. And now, how can I extend it to more general setting? Like I have a high dimensional density, I can break it in blocks. So what can I do? Well, that's simple. You just have to calculate the conditionals, and you apply the condition importance sampler to each of the blocks. And then you iterate it as a Gibbs sampler. So instead of sampling from a proposal, conditional proposal, you construct a conditional importance sampling approximation to each conditional, and things work. Okay, as I said before, in importance sampling, you can frequently apply variance reduction techniques. and they are extremely helpful in reducing the variance of our estimates. In MCMC, it's a little bit more challenging, as in sometimes you can't really do it in an efficient way. I also said that we are wasting computational costing calculating the proposals, the approximations. Well, that's not really true. As I said, we can reuse it. And it means that we can use all the particles generated by the system to calculate moments. By doing that, we can improve our approximation. And maybe the two most interesting applications are, first, row localization, in which we don't really need to know the condition distribution, as we already have an approximation to it. So we have an approximated Rao-Black localized estimator. And that's actually quite neat, because in many settings, you cannot really do it. You cannot really do much. Alternatively, we can use, well, which is actually quite useful, we can use contravariates, which boils down to, instead of estimating only our target moment, we combine it with highly correlated variables. So what will happen is, with zero means highly correlated variables, and what will happen is that the contravariate estimate will have a lower variance than the original one. Well, is to say, does it really work? Well, it does. I have a couple of examples. One of them is a bivariate Gaussian toy model in which I'm sampling x1 condition x2, x2 condition x1. If you have ever worked with Gibbs sampler, you can actually control the autocorrelation of the chain by changing the correlation between x1 and x2. We want to compare the ideal Gibbs sampler. We want with the Gibbs sampler using metropolis within Gibbs with a T5 proposal with same mean variance as the target. We also compare with the Gibbs sampler with cross-validation, which in this case is possible because we know all the conditionals, and we have two of our methods implemented. Okay, good. Okay, so let's compare. Here are so I'm calculating the mean square error based on 500 replications of Markov chains of size 10,000. The computational cost is normalized, so that we run the chain long enough so that the computational cost is exactly the same for each algorithm. Now, the Gibbs sampler is the ideal Gibbs sampler, as we all know, because we know all the conditionals. Finally, the Gibbs sampler with cross-validation is the one with contravariates is the Gibbs sampler. We use the contravariates approach by Petros de las Portas and Konstantinidis, another Greek guy, I can't pronounce his name. And metropolis within Gibbs is what we are trying to propose a new alternative. And then you have two of our algorithms. The last one is we are estimating these moments, these statistics here, these moments here using contravariates, and our Markov direct importance sampler uses antithetic variables. As we see in a low correlation setting, we do improve compared to the metropolis within Gibbs and ideal Gibbs sampler, but the Gibbs with cross-validation is just really unbeatable. Is what we really want to do. That's our target. That's what we really want to do in general settings, which is not possible, only in very particular settings that you have all the conditionals. But you see that, well, we do improve a lot, but if you have highly correlated setting, we are almost there. Our result is almost as good as the ideal one, and that's using 50 particles. I have one more example, but I'm not sure I have time. 20 seconds, I don't have time. Well, but I'm just going to show you one thing, is that algorithm is also very robust. When you start from, initialize from the prior, here's a very complicated Poisson process. And even starting from the prior, we have, like our method works quite well. Okay, so that's a brief summary. I can answer questions, I think.
Questions?
Hi. First of all, nice talk.
Thank you.
At least I enjoy your talk. And I have to say the truth that by your presentation, I understand that I didn't understand nothing about your work in my previous read, because I also already cite your work. Because I was also afraid that was quite similar to something that I did.
It's very different. I read it.
Okay.
Yeah, I read this morning, actually.
Okay. So actually, I think finally that your work is, your algorithm is an NCMC, actually, and in our work is an important sampler.
Yes.
But, so I tried to understand what you are doing, and my question is, it seemed quite related to the MTM, the multiple try metropolis.
Yes, it is.
So what is the difference?
Okay, so there are a number of differences, and I'm going to be very brief. In the multiple try metropolis, you have something called the reference set, and then you revalidate or not this reference set. Okay, you have alternatives that you don't have to resample the reference set, but even there, we couldn't really find a way to use all the variance reduction techniques like naturally in there. And the reason is because we have that Markov, the Metropolis Hastings jump. So we have this jump. We can either stay in the state or jump. In our case, we have all we have is just a conditional on the current state. We have an important sampling approximation, and we managed to do this case. So it's very possible that I don't have enough knowledge deep enough in multiple try, so I couldn't really apply. But we also did implement multiple try, many versions of the multiple try, and our algorithm managed to win every time when normalized by time. So except when we use proposals that were independent proposals. In this case, we got, was a tie.
Okay, but I think it's quite interesting for me. Another reference that maybe we can talk later is the ensemble MCMC or something like that from Radolf Neve that look also similar, but maybe we can talk about that later. Okay.
Yeah, so I have the whole theory developed, and so, it works, and we prove it works, and we show under all the conditions it works. Okay. So we did the whole theory, and there's a lot of also some extensions that are done that I couldn't really mention. But we can talk later.
Yeah, I think it's quite nice.
Well, thank you, Luca.
Okay, maybe in the interest of time, we could take the other questions offline and move on to the next speaker. Yeah, you can. No, that's fine. I think, or does anybody else have a quick question that they'd like to ask? Okay. So let's thank the speaker again.